Alright, I will start on magnetism. Okay, before going to magnetism, I think one or two applications what we were discussing for coordination chemistry I will show in here. Okay, sometimes we don't realize that the simple high spin, low spin configuration can give you something very, very important. For example, let's say you have a complex which is low spin. It has one color. Low spin, you know what sort of transition you do expect. It can vary depending on the compound. Let's say you have a given compound, the compound is low spin. If you give the temperature, if you heat the complex, what you can have is you can convert the low spin compound into high spin. Because low spin means what? Those spin cannot go in the Eg orbital, let's say, T2G to Eg orbital. Now, as soon as you put heat or let's say laser light, some of the spin, some of those electrons will be now traveling to the Eg orbital, T2G to Eg. Now the color of that compound will be different. It could be white to red, red to white, or whatever it is, right? So by changing these, something like display you see, lot of these color display, in big audience or big auditorium or even display in the on roadside somewhere else. So basically, let's say it's one color. The moment laser light is shining on this display, what happens? It may be showing a particular thing, particular let's say name written, whatever you want to, happy birthday wish, that's something you have wished me, that can be written over here on the board just by shining those laser lights. That is nothing but changing high spin to low spin configuration. Lot of things can be done and it has been done, okay, without realizing we are seeing those. Okay, other form of this sort of high spin low spin configuration can be used in your money card or ATM. Let's say you have a debit card, you have 10,000 rupees. Every time you pick up money, let's say first time you pick up 2,000 rupees from ATM machine, right? Now, so what can happen is a selected amount of laser light can be irradiated on your card because 2,000 rupees will, let's say, be selecting by default how much laser light to shine. Thereby, some of the complex will go from high spin to low spin or low spin to high spin, let's say low spin to high spin. Specifically, you are putting light, so low spin to high spin will be going. Next time, when you are punching the card again, the machine can read how much money you have left. Let's say after 10,000 minus 2,000, 8,000. This way, let's say at the end you have 1,000 rupees, you want to draw 5,000 rupees from that, instrument will not allow. So these are also technique, these are different ways to take advantage of this complex. This is something one paper has already come, and only problem is so far this technique is little bit expensive. That's why we don't see it in the market right now, but soon enough it will be hopefully made cheaper, and then you can, the technology itself is coming expensive, that's why it's not in the market, but in principle it can be done. So lot of the practical application just by shining light, since just by shining light you can change the electronic configuration of a compound. Of course you have to choose the right compound, right wavelength and right everything, let's say. But once you have that right combination, you can do wonder. Something like this, right? Also other thing, of course, you know that you have a colorless compound, you add something, high spin to, let's say, low spin complex form, or low spin to high spin complex form. Something like, you cannot read here, this is a iron aqua complex which is colorless. The moment you add phenanthrol into it, high spin complex becomes low spin complex, color changes. Okay. Another, so this is, of course, sometime you can use it for magic, lot of other application you can have, simple color change. Other things, for example, if you have, let's say, this red complex, Okay, rate complex is due to the low spin complex. Rate complex is due to the low spin complex. For example, you are starting with that. You are heating it. Okay, so this is the temperature. Initially, it was 250 Kelvin. Okay, that is almost like room temperature, let's say. Okay, you start from there. You keep on heating. Nothing happening. Nothing happening. At a selected temperature. Now, the low spin to high spin transition is going on. Then what you will see, all of a sudden at a particular temperature, this red compound is becoming white. Okay, so at that, let's say this is 325, this is becoming white. Now that white compound, you can try to cool down, it will not follow exactly same pathway because the relaxation of the spin, like spin was up, spin has to go down, that relaxation need not be necessarily following the same path. You have excited something, the relaxation means coming back from the the EG level to T2G level need not follow the same temperature profile. What it can happen is after reaching this white color, it will take quite some time to come back to the red color. So that even if you are decreasing the temperature, still it stays white, and at a particular temperature, cooling down at a particular temperature can bring you red. So these are nothing. This is like a very good, these sort of behavior you can apply to something which may be, let's say, it could be, let's say, what I said for money card, your ATM card, it could be for other display device, lot of other things you can do. So display device, for example, it is here, you just shine the light, so it is getting heated, thereby, so red color or let's say purple color, it is coming white color. Even if you cool down significantly, this white color may not go back to red very quickly. But then again, there are different material which can relax faster. That means high spin to low spin, it can come down faster. So you shine the light, whatever writing is there, you see it. You take off the light, it goes back to the white, red or blue, this purple again. So you can basically dictate the term. You can tell what you want, thereby which complex to pick. You want to shine the light from, let's say, violet color or red color. You want to go to white color, and you want to stay in white. That is one of the mode. Or if you want to go back right after switching off the laser, that can be also possible. So these are nothing but application in different display which you can have based on the synthetic chemistry knowledge. Of course, lot of startup companies and lot of other related application in material science has already come up. These are something, of course, you can in future if you are looking for a startup companies. Okay, something that this knowledge, it not necessarily this knowledge, it's some other knowledge you read in, let's say, in fourth year. So you can take it off and try to set up a company from these simple ideas if there is none existing. So that's, I guess, that's the knowledge sharing. And today we will discuss mainly magnets. Okay, we were discussing magnets in the last class. Simply, magnets are nothing but having, or magnetic compounds are nothing but having unpaired electrons. That's what we were discussing. More than unpaired electron, better the magnetic moment, or higher the magnetic moment. Magnetic values will be high. Okay. If you have paired off, all the spin paired off, if you have unpaired electron, but those unpaired electrons are not unpaired, they are pairing it up, then you are losing the magnetic values, right? Magnetic moment value. So all the complexes can potentially therefore give you magnetic moment because all of them are having electrons. Now the electron, as we were saying, electrons are rotating around its own axis. That's the spin value. It's spinning. That's why it can give you one type of momentum, okay, or spin angular momentum, or sorry, it is called spin only values for magnetic moment, or it can rotate around the orbital. Okay, there is a nucleus surrounding it, the electrons are rotating. So these are the two types of motion that can give you magnetic moment. But what we are saying usually, you don't have to worry about the orbital component. Only the spin only value good enough, because ligands are restricting the electrons, because they are overlapping effectively, restricting the electrons to rotate around the orbital. So therefore, since the electrons cannot really, valence electron mind you, not the inner electron, valence electron not effectively able to rotate around its own orbit or rotate along its orbit, you end up getting only spin component, only spin magnetic moment value you get. Okay. Now also we were trying to tell you that some cases you have to have spin value plus some orbital contribution. Why is that? That's simply because those, whenever one orbital to another orbital transition is possible, I guess last class we were trying to discuss. So let's say dxy to dyz to dxz, these transitions are allowed transition, because by rotating just 90 degree you can interconvert these orbital. Therefore, you can see there is a magnetic component, let's say from xy direction to a xz direction. So thereby there is a some sort of magnetic contribution on those z direction. It's not necessarily ligand is holding the electron completely. It's retarding it, it's preventing it, but not 100%. The moment electron can transfer from one orbital to another orbital, that means the direction changes. xy direction to xz direction. Z direction, some component will be arising. That is the one going to give you the orbital contribution. Okay, I will come back to that again. Okay, let me tell you again. Simply electron can spin, therefore magnetic moment values can come out of it, but opposite spin can cancel each other, as we were trying to say. Okay. Overall, I guess overall we, in terms of mathematical calculation, we can have this equation where essentially you are keeping your molecules in a magnetic field, and that magnetic field is going to be your H. So let's say this is the magnetic field of H. Here you are keeping the compound, right? So how much magnetization or how much effect this molecule is going to feel, that is dependent on the magnetic field, that H, plus its characteristics, its nature. What can it be magnetized pretty easily? That is the term called I. Okay, so any species kept in a magnetic field is going to feel the field itself plus its inherent behavior that will try to make it magnetized. So that is the I component. Now, so intensity of magnetization, how quickly it can or how greatly it can orient with respect to that magnetic field. Okay. Now, if you do the math, so B by H, if you divided by H, B by H will be 4 phi I by H, right? This term is called this kappa, or the magnetic susceptibility. Okay, so this is the term, kappa is the magnetic susceptibility. Now from there you can do the following math. Simply there is kappa by rho, which is the density of the species, density of the molecule, that will be the gram magnetic susceptibility. Multiply that with molecular weight, that will be molar susceptibility. So this I by H term, you divide it by rho, simple, its density of the molecule, you get chi g, or x, this magnetic susceptibility, gram magnetic susceptibility. This term you multiply by molecular weight, you get molecular, or this molar susceptibility. Okay, this is just simple math. You have this equation, divide by H, you get I by H, which is kappa. Divide kappa by rho, that is going to be your gram susceptibility or mass susceptibility. Mass susceptibility multiplied by molecular weight, you are going to get the molar susceptibility. It's something I think you have studied before. Now, once you have that molar susceptibility, that is corresponded with the magnetic moment value. This is the simple equation. Now, from there you can get the magnetic moment value of a compound, right? Of course, mu you can calculate what it is coming, it has a temperature component. So, what it tells you is the temperature is going to affect your magnetic moment value. We are going to see how it is affecting. The magnetic moment value is the one we were talking, it has two components, okay? That spin component and the orbital component, okay? Now, this magnetic moment value can give you the idea about the complex itself. What it is made of, how many unpaired electron it has. This is a experimentally measurable quantity. You can measure the magnetic moment value and thereby you can get crucial information about your, let's say, unknown compound. Okay? It can give you number of unpaired electrons present, high spin, low spin. It can give you the spectral behavior. It can also tell you something about the structure of the complex. So, what all we are saying is, if you have an unknown complex, you can measure the magnetic moment value of it, and thereby you can try to tell what that compound is made of, right? How the equations are, we have seen in here. These are two different equations. One is this one, another is this one. As long as you know the relationship between these two equations, you are good to go. This is simple connection between them. You just figure it out between these two equations, this equation and that equation. Okay? They are connected by this kappa I by H, and then kappa divided by your density will give you molar susceptibility, and then multiply by molecular weight. You just look 2 minutes, it should be clear. Right. So, based on these equations, it is expected usually one of the math is given. Usually we get one question at least based on these two equations. Their interrelation, some value will be given, and thereby you have to calculate the magnetic moment, let's say. Okay. Usually also in I think maybe it's in the tutorial question as well, I forgot. Okay. Fine. Now, we were talking in the last class as well, and today itself also, we have two component, orbital component and spin component. The resultant one is going to be the mu total, right? But this orbital component is going to be nullified, or it will be diminished, decreased, not necessarily you can prevent it 100%. Okay? That is the orbital contribution. Usually we do not have to worry about orbital contribution, you can calculate just mu spin only. The equation for calculating this mu total by taking this orbital and spin contribution is this one. Okay? Alright? Now, what happens, so the capital S, this S is number of unpaired electron, their spin. If it is 3 unpaired electron, half plus half plus half, 3 by 2. L will, that will come for the lanthanide section. It is the summation of usually ml, right? So for d orbital it is, let's say, +2, +1, 0, -1, -2. Will come for the lanthanide, from there we will discuss. Anyway, you don't have to calculate for d block element. You usually do not have to calculate the L values. You can only plug this equation for the S value, okay? Okay? Alright. So, we have two component. Once again, only spin value is good enough. What you nail it down further is root of n multiplied by n plus 2. N times n plus 2, root of that. That gives you for 1 unpaired electron, 2 unpaired electrons, 3 unpaired electrons, 4 and 5 and so on, what would be the magnetic moment value. So by knowing how many unpaired electron is there, pretty much you can be confident what will be the experimental or experimentally observed magnetic moment for pretty much a lot of cases. Now, so that's the magnetic moment value, but often what you see is at the end of it, the experimentally observed magnetic moment value is slightly higher, sometimes lot higher. How those are coming from or where they are coming from. That is due to the assumption that this component does not exist. Okay? We bring them back to explain it. Okay? So when you need to, when the orbital angular momentum, that mu L part comes in, okay? It comes in when you have degenerate orbital. We have degenerate orbital. If d orbital was not splitted, then this component would have been high. If 5 d orbitals were degenerate, then interconversion would have been possible much easier. Or 5 of the orbital, it can interconvert. So electron can interconvert between 1, 2, 3, 4, 5. So therefore, the orbital angular momentum value would have been higher. Since in octahedral field, for example, or tetrahedral field, it is splitted into T2G Eg or ET2, we are going to get little less orbital angular momentum value, okay, compared to unsplitted d orbital, right. Now, of course, interconversion leads to some sort of new directionality, xy to xz, z is new, xz to yz, y is new, right. So that is the one contributing for your little bit more momentum, right. Now, just degeneracy is not good enough. Why? Because you should be able to interconvert also. For example, dx to y2. Okay, this is the last warning. Okay, it's a big class. If it was a small class, I would not have mind too much because I know what exactly goes on. Okay, please have some respect. Okay, so what we are trying to have is T2G Eg. Eg dx to y2 and dz2, by no way you can interconvert. Therefore, in Eg, from Eg you cannot get any orbital angular momentum value. Only possibility is T2G, because the dxy, dyz, dxz are interconvertible. Okay? Of course, if they are having same spin, you cannot interconvert, right. So let us say T2G3, 1, 1, 1, all three of them are having same spin, you cannot interconvert, fair enough. So there should be similar shape in size, dxy, dyz, dxz are the same shape in size, they should be interconvertible, and the orbital must not contain electrons of identical spin. That's the criteria for getting some orbital angular momentum. Is it clear? So T2G1 you can get orbital angular momentum, because T2G1, that one unpaired electron can be either in dxy, dyz or dxz. 3 different orientations are possible. T2G2 is possible, T2G3 is not possible, T2G4 once again is possible, T2G5 is possible, T2G6 is not possible. Okay. T2G3, all three are having same spin. From where to where you will interconvert. See, T2G1 means dxy to dyz you can go. Interconvert means one means they have to exchange. If there is no scope for exchanging, how will you exchange? Okay. Same spin, T2G3 means 3 unpaired spin in the same direction. Spin multiplicity, same direction they will be having. So only so far as you see, only T2G3 will not be able to give you. Yeah. Okay. Yeah. that I'm coming. Yeah, next slide. So that interconversion will be having some contribution, not as great as let's say T2G to T2G configuration. So T2G to T2G interchange will give you little bit more orbital angular momentum value compared to EG to T2G conversion. That's what the next slide is all about. So dyz, dxy and dxz, these three orbitals are interconvertible, no problem. Okay. Over here, that's the interconversion is shown. So you just rotate by 90 degree, you will be able to rotate dxy. So this plane to that or whatever, these three different plane you can see. Now as you see, dz2 and dx2 y2 are not interconvertible. So purely from EG orbital, just EG orbital itself cannot give you any orbital angular momentum value. So the spin only value is only considered. Okay. Now of course what your friend trying to say is dxy is can be converted to dx2 y2. Yes, and thereby once you can convert dx2 y2 into dxy, then you can interconvert dxy to dxz, dyz and so on. So T2G EG mixing if you can have, then you will be able to get better orbital angular momentum value. But usually for mixing, those energy has to be close enough. If the gap is very high, that mixing is not going to be possible, right? Okay, so we all hopefully by now understand that it is angular momentum or this orbital angular momentum and spin momentum value are important. Usually spin only value is good enough, but in some cases you have to talk about orbital angular momentum. Actually that makes it little bit important or interesting. Otherwise whatever unpaired electron is there, you will just end up calculating based on your calculator, right? That's not fun. Of course the exam questions are asked at least 1, 2 or so on orbital angular momentum. Okay, when orbital angular momentum is there. Okay. Now, so this is the same thing what I was trying to say. D1 can have these three different contribution. For example, titanium 3+ is having D1 electronic configuration, and therefore orbital contribution will be there. For example, D2 vanadium 7+. So how the question would be, let's say a complex is given where vanadium 3+, and you are asked whether it will have any orbital angular momentum or not, or in some other form it will be asked indirectly. But mostly, definitely I can assure you at least one question will be there on orbital angular momentum, at least, if not two. Okay. So there you can have 2 different or 3 different configuration, orbital contribution possible, yes. Okay. Now this is something you do not have to remember, but you can justify. You can go through each of those one by one. So D1 orbital angular momentum possible, yes. You can perhaps not read from here, that's okay. So what we have tried to do here is given you the complex, different complex and their electronic configuration D1, D2, D3, D4 up to D10, and then you have to write down T2G EG electronic configuration.